Welcome to the Crazy Hat Chemist. So here we are working on the next unit here, and this is all about solutions. Well, chemists have all the solutions to all the problems that you might have. And I'm sure you only have just a couple of problems, but let's uh, let's assume that you have at least one problem. So here are the solutions to all your problems right here. So I'm going to make a few assumptions here before starting off with this, and I'm going to assume that have a strong foundation in nomenclature, um, and you are also going to be having a periodic table. I will be using this specific periodic table. It comes from the SAT-2 subject test in chemistry, and you have a calculator with you as well, hopefully. And so without further ado, we're going to go over this sheet of paper right here in the front here. And this is going to have just a bit of a summary here before we end up going into the solutions of each problem on the properties of solutions. So I'm going to zoom in on this and then let's get moving here. So here we go. So a few things here for this unit on solutions. So here we have molarity. Molarity is a capital M. And what is that? So we're going to break that down, and it's the moles of the solute divided by the liters of solution, okay? And that's different than molality. And notice that this is a capital M and this is a lowercase m, and that's why this is a capital molarity and this is a lowercase molarity. Not that the name is different in regards to the capital and lowercase, but the capital M deals with molarity, moles of solute over liters of solution. Molality is a lowercase m, and that's moles of solute over kilograms of solvent. So we're going to figure out what the solute and the solvent is in just a moment here. Okay, but what's similar between these two is that the numerator is the same for both. That is, they both have moles of solute. Where they differ is in the denominator. And so the denominator for molarity has liters of solution, and the denominator for the molality is kilograms of solvent. So what's really important is that molality gives you how many particles are in that component, and that's really an important thing. So this is something to easily remember. The solution is equal to the solute plus the solvent. And if you look at the number of letters in each of these words, solution has 8 letters, solute has 6, and solvent has 7. So you can tell your math teacher that 6 plus 7 is equal to 8. You can also understand that solute has the fewest number of letters at 6, and the solute is always in the smaller quantity. And solvent has 7 letters, so it's in the greater quantity. And the sum of these two is equal to a number that has a larger, and that would be the solution. So hopefully that makes sense. This has 8 letters. It's the larger number of letters. It's the sum of the solute and the solvent. Just make sure that you know the solute is in the lesser quantity, the solvent is in the greater quantity. All right. Then we're going to go into dilution problems. And hopefully you're familiar with doing any kind of dilution. You probably do lots of dilutions in your life. And that could be you have maybe some concentrated orange juice or some concentrated lemonade or something like that, and you dilute it with water. But as a chemist, we do this all the time. So this capital M goes back to molarity, and this V is for volume. So M1 V1 is equal to M2 V2. And it does not matter what you use for the volumes. You could use any volume you want to. You do not have to use liters. You can use milliliters, provided that both the volumes are in the same set of units. So you're probably pretty good there. So just so that you know. Now that we are coming from like the gas unit where it had to be in liters. This does not have to be in liters. It can be in any units of volume, and that would be fine. But this does have to be in molarity and not molality. We have Henry's law of solubility of gases in solution. So this lets you know how soluble a gas is in solution, and that's dealing with Henry's law. And this is one way of writing Henry's law in a ratio, and that is the solubility of a gas over the pressure of the gas is equal to the solubility of the gas over the pressure of the gas. And condition 1, condition 2. I'll go over some problems with that, and then hopefully that will make sense. Another one is percent solutions. And so this is the percent solute. And how you get that is the percent solute is equal to the solute over the solution times 100. You can also do the percent solvent, and that's right here. Percent solvent is equal to the solvent over the solution times 100. Notice that the numerator portion changes on these right here, okay? And that's important. Another one that's important in this unit is the mole fraction, and that will be dealing with Raoult's law, which I won't be getting into in this unit here of solutions. That's more of an AP chemistry problem. So the mole fraction is a fraction. So it's the mole fraction is x of A, and so that would be moles of A, whatever component A is, divided by the total number of moles. So that's moles of A plus moles of B. This is assuming a two-component system. You are not multiplying by 100 because it's not a percentage, it's a fraction. So this number right here, the mole fraction, must be less than 1. Another way to look at that is the moles of A divided by the total number of moles. So you could have a three-component system. So it would be moles of A plus moles of B plus moles of C. That would work. If you wanted to get mole fraction of B, then it would be moles of B over the sum total of moles, and that would be moles of A plus the moles of B. Again, so got mole fraction of A and mole fraction of B. If it's only a two-component system, then the mole fraction of A plus the mole fraction of B would equal 1. And so that's another way to work on those problems. Let me scroll this up just a little bit so that we get a few more parts to this, and that will be very important here. Okay, so I think that will give us a good summary here. So the next one is going to be the boiling point equation, and the boiling point equation is the boiling point is equal to the normal boiling point plus the change in temperature of the boiling point. Okay, and the normal boiling point is whatever that normal boiling point is for the solvent. Okay, so the solvent is the normal boiling point. And the delta TBP, that's the change in temperature of the boiling point, that's generally viewed as the final temperature minus the initial temperature, okay? And the change in temperature of the boiling point, the change in temperature of the boiling point is equal to Kim, K-I-M. I always tell my students that Kim was one of my girlfriends in college, and you just have to figure out, is that her first name or her last name? But it's one easy way to remember this. Many textbooks actually rearrange these letters and put it an I, a K, and then an M. But Kim would be much easier to remember than I-K-M. What does that mean? Who knows? But Kim is important because Kim is a name. So Kim, the K for Kim, is the boiling point constant for the solvent. That's a constant. It's the boiling point for the solvent, the constant for the boiling point of the solvent. The I is called the Van't Hoff factor, and that's for the solute, and I'll talk about that in just a little bit. And M is the molality. What is the molality? Well, we just talked about that up there just a moment ago, okay? And then we have the freezing point equation. FP is for freezing point. The freezing point is equal to the normal freezing point plus the change in temperature of the freezing point. Actually, what we're going to do is, depending on the constant and what that is, then many times this right here is going to be a negative sign. So I'm going to change this to a negative sign for our purposes here. And it depends on what the textbook gives you. If the textbook gives you the freezing point constant as a negative value, then you would have this as a positive. It just happens to be that my textbook has a positive value for the boiling point constant and the freezing point constant. So if it's the freezing point constant is a positive value, then we're going to do a negative. And so what you need to remember is that the boiling point is always going to be, when you add a solute to the solvent of a solution, you have a solution, then the boiling point will always be greater than that of the normal boiling point because you're adding. And the freezing point will always be less than the normal freezing point. So that's why we're going to have a minus sign right here, unless the constant already had a negative sign in front of it, okay? And so our change in temperature of the freezing point is equal to the K, the constant for the freezing point of the solvent, the I, which is, again, the Van't Hoff factor. It's the same one as what you have for the boiling point, and times the molality. the same equation effectively that you use for the boiling point. So notice that there's not much difference between these here. Okay, and then the Van 't Hoff factor, what is that? It's the number of particles in solution. And so if you have a salt, an ionic compound, then you're going to get the number of cations plus the number of anions, and that will give you the Van 't Hoff factor. If you have a binary non-metal compound that uses prefix naming, like nitrogen dioxide, carbon dioxide, nitrogen monoxide, dinitrogen pentoxide, those all have a Van 't Hoff factor of 1 because that's a molecular compound and that does not dissociate. If you have something with carbons, hydrogens, and oxygens in that formula, then the Van 't Hoff factor is also 1 because that is a molecular compound. It does not dissociate. So that's why it's really important that you need to know your unit on nomenclature. And if you remember back to the nomenclature unit, in the nomenclature unit, the Van 't Hoff, you were taught really the Van 't Hoff factor, but kind of under the background there. And that is truly the number of cations plus the number of anions. So if you follow along with my worksheet here, I'm going to go over that a number of different times. So hopefully that will be helpful. All right, so this will give you a summary of all the equations that you need within this unit here. So hopefully we'll be coming back to many of these within the problem. So without further ado, let's get moving on to some of these problems. So here we go. Let's see if we can get this set up here for you nicely. All right, perfect. All right, this is solutions worksheet number 1 and the stepwise solutions of these. Okay, all right. So let's see here. We're going to read this problem. It says, number 1, suppose you have a 0.15 moles of calcium chloride in a 125 ml solution. Calculate the molarity. That's the capital M. Okay, so you can do these problems a number of different ways. Okay, there are lots of different ways to obtain the correct solution to your problem. Hopefully you get the pun there. But I'm going to show you many times just one way. So here we go. So molarity is the moles of the solute over the liters of solution. Okay, and it says that it's a 125 mils of solution. So that's actually going to be my denominator term. But molarity is moles of solute over liters of solution. Okay, so that's just your basic equation right there. So what we're going to do is we're actually going to plug into this equation, and that way we can solve for this. Let me get a ruler here, and hopefully that will be helpful. Yes, all right, fantastic. All right, so we got our ruler here, and what we're going to do is we're going to come up with a numerator term and a denominator term. Okay, and the moles of the solute. The solute in this case is going to be the calcium chloride. Okay, and calcium is a group 2. It's a +2 charge. Chloride is a halide ion -1. You're going to take the absolute value of these two here, flip them and bring them down, and then you get the correct formula for calcium chloride as CaCl2. And so I had talked about the Van 't Hoff factor before just a moment ago when I gave a summary. And now I'm going to come up with the Van 't Hoff factor for this, and so that you understand. And then when we get to a boiling point or a freezing point problem, then you will understand what the Van 't Hoff factor is and how to obtain it. So how many calciums do you have? Well, this is 1. So there's 1 cation in this formula. How many chlorides do you have? There's 2. So we're going to add up the number of cations plus the number of anions. That's 1 plus 2. So the Van 't Hoff factor, that is a scripted I, is equal to 3 for calcium chloride. Now, just so that you understand this, and I do mention this in my lecture, and I'm hoping that you have watched my lecture on properties of solutions. The entire lecture, I have it in a playlist on YouTube, so hopefully you've watched that prior to attempting these problems because I give you the background information on that. Okay, but the Van 't Hoff factor here is a theoretical value. The Van 't Hoff factor in reality is always going to be slightly less than the theoretical value. We're using the theoretical value here. So That will be perfectly fine unless you are given it in a textbook problem and they actually give you the true Van't Hoff factor. Okay, so having said that, we don't actually need the Van't Hoff factor for this problem, but I'm going to give you that as we go along all these problems so that you have an idea. All right, so since it's moles of solute, the solute is the calcium chloride. Why is the solute the calcium chloride? Because water is the universal solvent. And we are going to assume that the solvent is water unless it's otherwise specified or other information is given in the problem to delineate that water is not the solvent. So we'll figure that out as we go. So we have moles of calcium chloride. So that will be 0.15 moles of CaCl2. And so that's going to be my numerator term because moles is in the numerator, and that is the solute. And then we have moles of solute. Now we need to get liters of solution. Well, we don't actually have liters. We have milliliters of solution. We have 125 milliliters of solution. So we're going to say 125 milliliters. And now what we're going to do is we're going to have to convert this into liters. And so hopefully you understand this short little conversion here from milliliters to liters. And that is 1,000 milliliters is equal to 1 liter. All right. So now what you're going to do is you're going to plug into your calculator the following. 0.15 divided by 125 divided by 1,000. So depending on your calculator, you could do this individually by itself. This right here in the denominator term is going to be 0.125 liters. So you could say 0.15 divided by 0.125. That would work too. Okay, and then you're going to get a numeric value in your calculator, and then you're going to have to round this. This is a multiplication division problem, so you're going to have to round this according to the fewest number of significant figures. Leading zeros do not count. Remember, this has 2 significant figures. This has 3 significant figures, and this has an infinite and an infinite because this is a definition. So the fewest number of significant figures I have on this problem is 2. So we're going to have, just like what we've been doing in the stoichiometry unit, we're going to have numbered units formula. So this is a 1.2 molar CaCl2. And then there is my rounded answer, right? So hopefully everybody's good with that one. And I've done that in a one-step process here. So, excuse me. All right, so let's move on to the next problem. So we're going to slide this up just slightly here, and we're going to move on to problem number 2. All right. So problem number 2, it says if you add 2.35 grams of calcium nitrate to water to make 250 mils of solution, calculate the molarity M. Okay. All right. So this is a very similar type of problem that we did on problem number 1, except we have different formula and we have different numbers, of course. Right. So a little bit more complicated, but not really too bad. So I'm just going to write down the equation for molarity. Molarity is equal to moles of solute divided by the liters of solution. So I'm writing this down again so that you can keep on remembering this and then putting this back into your brain every single time. So again, what is the solute? What is the solution? Well, I have 250 mils of solution. So hopefully that obviously goes in the denominator term. And then I have 2.35 grams of calcium nitrate. Well, I need to figure out what the formula of calcium nitrate is. And so calcium is a group 2. That's a 2+ charge, and nitrate is a polyatomic ion. You just have to memorize that. That's NO3 minus 1. You're going to take the absolute value of these two numbers here, flip them and bring them down, and then you will get the proper formula for calcium nitrate is Ca parentheses NO3 and A2. And again, what we're going to do is derive the Van't Hoff factor here for you on this problem as well. So how many calciums do you have in this formula? 1. How many nitrates do you have in this formula? 2. So how many cations? 1. How many anions? 2. I'm going to sum them up. That's 1 cation plus 2 anions. That's a Van't Hoff factor of 3. Notice that that Van't Hoff factor is the same as the previous problem, even though this one had a polyatomic ion in it. All right, so What we're going to do is we're going to draw effectively this nice line in the sand here. We're going to have our numerator and our denominator portions of this problem. So in the numerator, we're going to have our solute, which is the calcium nitrate, and it needs to be moles. So in the numerator, I'm going to start off with 2.35 grams of CaNO3 parentheses 2, okay? And so I'm going to have a numerator in a numerator here because we're going to be using a little bit of stoichiometry that we have used in the past, and hopefully you're familiar with that, okay? Uh, Perfect. All right, and so then what we're going to do is we are going to convert these grams into moles. Okay, and so this is using our periodic table that I had aforementioned, right? Here's our periodic table. We're going to find calcium and its molar mass, and that's 40.08. We're going to find nitrogen, its molar mass is 14.007. We're going to find oxygen, and that is its molar mass is 16.00. So hopefully you have that familiar to you, and we're going to have 1 calcium, 2 nitrogens, and 6 oxygens, and then we're going to get a molar mass with the fewest number of decimal places of the calcium, the nitrogen, and the oxygen. Calcium and oxygen both have 2, nitrogen has 3 decimal places, so I will have 2 decimal places for my molar mass for calcium nitrate, and that is 164.09 grams CaNO3 and A2, and that's the molar mass for calcium nitrate. Okay, good. And so now that is equal, since it's the molar mass, that is equal to 1 mole. So I'm going to have that up in my numerator. So that is 1 mole of calcium nitrate. So this quotient of 2.35 divided by 164.09 will give me my moles of the solute in the numerator. All right, now what we need to do is get the liters of solution in the denominator. So I'm going to take my 250 milliliters. Notice that this does not have a decimal at the end of this number, so that means that there's only 2 significant figures in that. And just like I did on the previous problem, I'm going to convert this into liters. So I'm going to do that really quick step right over here. And we're going to have 1,000 milliliters and 1 liter. All right, you should see that our grams of calcium nitrate are going to cancel out. We're going to have moles of calcium nitrate, the solute in our numerator. The milliliters are going to cancel out in the denominator section, and the units in the denominator are going to be liters. So it's really going to be 2.35 divided by 164.09 divided by 250 divided by 1,000. And you can do these in sequential steps if you want. 202.35 divided by 164.09, get a number. Right, put that in the memory of the calculator, and you got 250 divided by 1,000, and you can put that into the calculator too and get a number. That's perfectly fine. I'm going to look at significant figures on this problem here, and it looks like I have 3 significant figures here. This number, the molar mass, has 5 significant figures. This is infinite for the 1. This is infinite for the 1 liter, infinite for the 1,000, and 2 for the 250. So I'm going to plug this into my calculator. I'm going to have 2 significant figures for my final answer. And so that will be, I'm going to put this in exponential notation, and hopefully you can, you don't have to use exponential notation. You can put this in decimal form, but I am going to put it in exponential notation. It's 5.7 times 10 to the negative 2 molar, and CaNO3 and a 2, and then that is going to be my answer. In decimal form, that number would be 0.057, and the same units of molarity and calcium nitrate for the formula. Okay, remember that leading zeros don't count. It still has 2 significant figures no matter which one you look at. All right, so hopefully that worked out well for you. Let's move on to problem number 3. Remember, you are watching The Crazy Hat Chemist. If you are getting good information from this, if you are learning something from this, because I am truly all about the learning, and I'm hoping that my students learn. I'm hoping that you are learning chemistry, because chemistry is an awesome science. It has lots of real-world application, and you can get an excellent paying job in any country that you want if you become a chemist. So it's a great profession. So highly promoting chemistry. So what we're going to do is do problem number 3. So I'm going to slide this on up and we'll do problem number 3. Okay, problem number 3, it says determine the mass in grams of barium chloride that is necessary to make a 2.5 molar solution with a volume of 150 milliliters. All right, so let's just start off by getting the formula for barium chloride. Barium is a 2+ because it's in group 2. Chloride is a halide ion. Taking the absolute value of those, flipping it, bringing it down, I got a BaCl2. That is my formula for barium chloride. And again, I'm going to get the Van 't Hoff factor for all of us here so that when we come to that freezing point and boiling point problems, then you should be familiar with it. There's one cation and there are 2 anions, so it has a Van 't Hoff factor of 3. Now, not everything has a Van 't Hoff factor of 3. It just so happens that the 3 problems here so far have a Van 't Hoff factor of 3, which is the same in all of them. But don't think that all the Van 't Hoff factors are 3. Okay, fantastic. So I'm going to try a couple of different things here with this one here. So what we have is we have 150 milliliters. So if we know our equation for molarity, it is molarity is equal to moles of solute over liters of solution. Okay, and so what is the solute? What is the solute? It is, again, not the water. The water is the universal solvent. So we're going to assume that the solute is going to be the barium chloride here. That would be an excellent assumption. And we're going to determine the mass of the barium chloride. Okay, and so from moles, I'll come back to that in just a second. Then we have this 150 milliliters of solution. So it's 150 milliliters. So that is going to go in my denominator term. But I'm going to have to convert this into liters for it to go in order for it to go into my denominator. And then I'm given that it's a 2.5 molar solution. So this value right here is 2.5 molar. Okay. So what I'm really doing is I am going to be solving for X. And X is the moles of the solute. But once I solve for X, then I need to convert that to grams. And that will be using the molar mass. Okay, so I'm hoping that I'm setting this up for you. That is, this is the molarity. I'm going to convert this 150 mils into liters. So I'll do that really quickly here. 150 milliliters and 1,000 milliliters. 1 liter. The milliliters cancel, and I'm left with 0.15 liters. Notice that that trailing 0 did not count because there was no decimal at the end of this number. So this number has 2 significant figures. This number has 2 significant figures, and now it's in the correct units that need to go in the denominator. So what I'm going to do is I'm going to plug into this equation that I have. I have the number here for the molarity. I have the number here for the denominator, which is the liters of the solution. And then I'm going to solve for my numerator term. So I'm going to rewrite this here, and I'm going to have 2.5 molar is equal to X moles of BaCl2 divided by 0.15 liters. Okay, so this is what I'm going to be solving for. Okay, what is the denominator of 2.5 molar? Well, the denominator of this is a 1. So what we're going to do is we're going to cross multiply. Okay, and so X times 1 is going to be X. Okay, fair enough. So X is equal to the moles of barium chloride. And now I'm going to type into my calculator 2.5 times 0.15. And this has 2 significant figures. This has 2 significant figures. So both these numbers have 2 significant figures. I'm going to end up getting two significant figures. So 2.5 times 0.15, that is equal to 0.38, and that's moles of the solute, which is the barium chloride. So that's what we should have now. Again, remember that you're going to reread the question to make sure that you are actually truly answering what it's asking for. And it says, what's the mass in grams? Right now I have moles. So what I'm going to do is I'm going to rewrite this here. That's 0.38 moles of BaCl2. And we are going to convert this into grams using the molar mass of barium chloride. So again, I'm going to be using my periodic table. Let me grab that real quick here. Barium has a molar mass of 137.33. Chlorine has a molar mass of 35.453. Chlorine's molar mass has 3 decimal places. Barium's molar mass has 2 decimal places. So I'm going to end with 2 decimal places in my molar mass. So this is going to be 1 mole of barium chloride, and this is going to be 208.24 grams of barium chloride. And then I'm going to cancel out the moles of barium chloride, and then we're going to have 2 significant figures, and this has 5 significant figures, and this has infinite. And so I'm going to say 0.38 times 208.24 divided by the 1, and I'm going to get my number, and that is 79 grams of BaCl2. And I'm going to circle this. This is my answer. It has 2 significant figures, and it has my number, units, and a formula. Enough of that. Boom. Okay, so hopefully that worked out. Hopefully you're following along pretty okie-doke. All right. So we're going to slide this on up to the next problem. That is problem number 4 on this worksheet. Here we go. All right. And just as a quick little, again, advertisement here. Yeah, I am the Crazy Hat Chemist. You're watching my videos, and hopefully you're watching all my videos on YouTube, and you're subscribing, and you're getting a YouTube account for your cat and your dog and having them subscribe as well, too. So if they ever get bored on a rainy day, then please have your cat and your dog subscribe to my YouTube channel. I'd greatly appreciate that. So here we go. Next problem number 4. It says sulfuric acid. Oh my gosh. Sulfuric acid is coming from the sulfate ion. And that is all acids have hydrogens for the most part for this unit. And sulfate is SO4 2 minus. So that will be H2SO4. Okay. How many cations in this formula? That would be 2. How many anions in this formula? That would be 1. Van Hoff factor of 3. All right. Fantastic. Sulfuric acid, otherwise known as oil of vitriol, is the most widely produced chemical in the world. Hey, that's a thought. If you are looking to make a lot of money and you want to be supplying other companies, other countries with a chemical compound, then design a way to make sulfuric acid at a cheaper price than other companies, and then sell them. So, and then just throw me a little bit of change as you make that huge amount of profit. Okay, it's the most widely used produced chemical in the world. If you have an 18.4 molar concentrated stock solution of sulfuric acid, and you want to make 600 mils of a 1.5 molar solution, how much concentrated stock solution would you need? How much water would be necessary to make this diluted solution as well? So I'm going to just circle this right here, and I'm going to note something from your math class. And I had talked to one of my students, and that student had said, yo, Mr. Moprion, I love chemistry. It's logical. It makes sense for me, but I hate math. And I'm like, no, 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 no. I said, this class is an applied math class. And so you have to love this as well, because this is a word problem. And chemistry is all about doing word problems. So you have to use and love the math here as well in chemistry. So if you like chemistry, you like math. You have, they go together. Anyways, so using your math class, I'm hoping that you remember that this word of in English is really a multiplication symbol. So that should be telling you that 600 mils times 1.5 molar. That's an of. All right. And I had talked about the equations that we were using in this unit. And one of them was M1 V1 equals M2 to V2. Why? Because this is a dilution problem here, okay? And so what we're going to do is find out how much concentrated stock solution, that would be a volume, that you need to make up this. So our molarity is going to be 18.4 molar of our stock. We're going to solve for this volume. We could have called it volume 2, it doesn't matter. And we have a molarity of our diluted solution that we want, and we have a volume of that diluted solution that we want. And there is a decimal right there, okay? And so I'm hoping that you understand that this is concentrated. That is, this is a larger number than this number. So this is concentrated, this is diluted. This lower number is a smaller number, it's a dilution. This number is a larger number, it's a concentrated solution. Okay, this decimal right here lets you know that this number has 3 significant figures. This has 2 significant figures, and this has 3 significant figures. We're going to solve for V1. So we're simply going to divide both sides by 18.4 molar right here. Okay. And therefore the molarities cancel out, and I'm left with a volume that's V1 is equal to 1.5 times 600 divided by 18.4. That will be a volume. And since this volume is in milliliters, this next volume will be in milliliters as well. And that's going to be 49 milliliters of the 18.4 molar H2SO4. So that's how much volume, that's 49 milliliters of the concentrated stock you need. Then the next question would be how much water would be necessary to make this diluted solution as well? So our total volume is equal to 600 mils, okay? And then we have the solute, if you will, plus the solvent, if you will. And the solvent is going to be water. The solute is going to be the H2SO4. So really what we have is the solute at 49 milliliters. We're solving for the solvent, that is the H2O. And we have the total volume, and there's a decimal right there. That's in milliliters. Our units are both in milliliters, so that's good. So we're going to do a little subtraction here of 49 mils on both sides. And then we're going to solve for our volume here of this. And that volume of water, so the volume of the H2O is going to equal 551 milliliters of H2O, okay? And most commonly, these problems are additive in their volumes, but not necessarily so when you do some dilutions. So for example, if you were to mix an alcohol and water together, you could mix, 95 milliliters of alcohol, ethanol, and 5 mils of water, and you won't necessarily get 100 mils total volume. But for this purpose here, for this math problem, we'll assume that they're additive and they work out fine. All right. Okay, hopefully that worked for you, and hopefully you're understanding that stepwise solution. Now we're going to move on to problem number 4. Excuse me, that was problem number 4. Now we're going to move on to problem number 5. All right, so here we go. Here is problem number 5. Let me put this up here for you. Okay, and let's see here. For problem number 5, it says if you have a 1.40% calcium carbonate solution, how many grams of solute are required to make 125 grams of solution? So it says 125 grams of solution. How many grams of solvent, that is water, is necessary? So you're given the water as the solvent. You have calcium carbonate, okay? So calcium is a group 2. That's a 2+ charge. Carbonate is a polyatomic ion, that's CO3 2 minus. You're going to take the absolute value of these two numbers, flip, bring it down, and then reduce them. And so you're going to get CaCO3. Van't Hoff factor here. How many calcium ions do you have? 1. How many carbonate ions do you have? 1. So 1 cation, 1 anion. That's a Van't Hoff factor of 2. Yes. All right. Something different than what we had before, at least. So we should be good. All right, so now what we're going to do is we're going to write down the equation for a percent solution. So percent solution is going to be the following. So percent is equal to the solute over the solution times 100. Okay. That's not to the power of 100, it's just times 100. Okay. So what is the solute? The solute is the calcium carbonate. Okay. The calcium carbonate is the solute. What is the amount of solution? That's 125 grams. And I have a 1.40% of the solute. So this is solute. So it's percent solute is equal to the solute over the solution. So I'm going to plug into this equation. I have 1.40% is equal to X grams solute, which is going to be the calcium carbonate, divided by the grams, 125 grams of solution, times 100. Okay. All right, so what we have here is our simple math problem. We're going to simplify this, and we're going to divide both sides by 100. That will get rid of this 100 here and divide by 100 here. That will move this decimal place 2 places over and get rid of the percentage, okay? And then what we're going to do is, then we're going to cross multiply after that. So we're going to have 0.00140, and we're going to take 125 times that, and then that will equal X. Okay? And so X is the solute that we're solving for, okay? And let me just pull out my calculator here and make sure I got this here. So, oh, wait a second here. Yes, here we go. So, wait a second. We need to move this decimal place 2 places over. I made a mistake here. This is 0.014. Okay, not that other number that I had up there. Sorry about that. So 1.40 divided by 100 is 0.014. We're going to take 0.014 times 125. That will give me my grams of the solute, which is 1.75 grams of the solute, which in this case is the calcium carbonate. So this is one of my answers right here. Bam, that's one of my answers. It's the grams of the solute. And then it also says how many grams of the solvent, that is water, is necessary as well. So what you need to know is solution is equal to solute plus solvent. So the solution is 125 grams. That's the sum of the two. The solute is the 1.75 grams plus the Y, I'll call it Y solvent, which in this case is water, the universal solvent. And just so that you are remembering this, solution has 8 letters in it, solute has 6 letters, and solvent has 7. So again, this is when 6 plus 7 is equal to 8. Solute has the fewest number of letters, so it's in the least abundant component. It is in the least abundant in comparison to the solvent, which has more letters, so it's in the larger abundant component. And that means that this number, 1.75, is going to be less than this number over here, okay? And the solution is a larger number than either of these two, so it's the sum of those, both of them. So I'm going to subtract 1.75, subtract 1.75, and I'm going to get Y solvent, which is equal to water, and that's going to be equal to 123 grams of water. And remember, when you're doing subtraction problems, you're using the fewest number of decimal places. This 125 grams has no decimal places. This has 2, so no decimal places will be my answer, okay? So I have 123 is my mass of my solvent, which is the water, and I have 1.75, which is my mass of my calcium carbonate. That is the solute. All right, fantastic. We are moving pretty fast here. Well, I'm not sure if we're moving fast or not, but we are moving down that train track here and hopefully doing well. All right, so we're going to slide this on up here and we're going to do our next problem. So I'm going to move this on up here and we're going to now do problem number 6. All right, fantastic. Here we go, number 6. So number 6 says, what is the mass of solvent, that's the water, in grams of a saturated saturated potassium chlorate, and that's 26.0% potassium chlorate solution at 70 degrees that has 32 grams, 32.0 grams of potassium chlorate. So it's saturated. That means as much as can go in there is in there. It's 26% potassium chlorate. And you have 32 grams of potassium chlorate. This 70 degrees doesn't matter for this problem mathematically. That's just where I came up with the number. This is actually a graph, a curve, which has the amount of solute on the y-axis and the temperature along the x-axis. And at 70 degrees, the maximum amount of potassium chlorate that can go into a certain mass of water is 32 grams. So here we go. We have percent solute is equal to solute over solution times 100. So I'm going to plug right directly into this here. Okay, I have a 26.0% is equal to 32.0 grams over y grams solution times 100. Okay. So the first thing that we're going to do when we do this, we're going to divide both sides by 100, and we're going to get rid of our percentage there consequently, and then these 100s right here. And then I have 0.260 is equal to 32.0 divided by y. And this, the denominator of any number is 1, so I'm going to cross multiply right here. So I'm going to have 0.260y is equal to 32.0. And then we're going to divide both sides by 0.260, 0.260. And I'm going to have y is equal to, and I will have my 123 grams of solution. Okay, so that is the mass of solution that we have. And so what we're going to do is we're trying to find what is the mass of the solvent. I actually haven't answered the question yet. So what I have to do is take solution is equal to solute plus solvent. Okay, the solution is 123 grams. The solute is 32.0 grams, and the solvent is going to be X, and that is going to be the water. So I'm going to subtract 32.0 from both sides, and X H2O, that is the mass of the solvent, is 91 grams of H2O. And that is my answer. Fantastic. Hey, I'm going to show you another way to do this mathematically. I'm going to set it up for you, and if I would highly recommend that you give this one a try as well. I'm not going to write it out here for you and do the whole solution of the problem, but I'm going to at least set it up for you. Okay, and this will work mathematically as well also. So we do know that the solution is equal to the solute plus the solvent. So we have 26.0% is equal to 32.0 grams of the potassium chlorate. And I need to write down that formula here for you in just a second. Let's see, potassium is 1 plus. Chlorate is ClO3 1 minus, so it's KClO3. So there's 1 cation, 1 anion, a Van 't Hoff vector of 2. All right. Now, what I had in the bottom here in the denominator before was solution. But what I can do is figure out what is the solution. The solution is equal to the solute plus the solvent. So what? The solute is 32 grams. The solvent is the water, X times 100. So this will also enable you to get the correct answer. And in fact, if you use this method, you can directly solve for the 91 grams. So if you solve for X right here, you will directly solve for the 91 grams right away. And that would be perfectly fine too. You get that without finding out what the solution is. And if you needed the solution, you would have to add the solute plus the solvent because that equals to the solution. So give this a try mathematically. What you would do is divide both sides by 100, and then you're going to have 0.26, and then you're going to cross multiply, and then you're going to have 32 plus x is equal to 32. And you're going to have to distribute this 0.26 over both these terms, separate the x terms and the non-x terms, and that's your answer. And your answer will be directly solving for the 91 grams. Right? Just so that you know. All right. So let's move on here. We're going to do problem number 7. All right. So let's do problem number 7. Fantastic. Boom. I can't remember how many problems we have on this worksheet, but we have quite a few, which is a good thing because you definitely need lots of practice. There are actually 19 problems on this worksheet. So that's a whole bunch of problems. Okay. This one says, what has the lower freezing point, 0.30 molal NaCl or a 0.25 molal of potassium iodide? Okay, so lower freezing point. So first of all, we got to figure out what this question is actually asking. So we don't actually have to calculate what a numeric value is of the freezing point for either one. So the freezing point is equal to the normal freezing point minus the change in temperature of the freezing point, which is equal to Kim. Okay, so we'll have to make an assumption here on both of these that they're both in the same solvent, which would more than likely be water. And since the constant is based on the solvent, what we're going to do is compare these two things together. So one of these is going to be for the NaCl. One of them is going to be for the Ki. Okay, so we're trying to figure out which one has the lower value of these two. Now, since we're going to make the assumption that the solvent is water, that means that this normal freezing point for water would be 0 degrees Celsius. Notice that the normal freezing point is the same for both. Okay, got that. Since they are both in the same solvent, that means that the constant is the same because the constant is based on the solvent. So really what we're looking for is whichever one gives us the biggest Kim, the largest value of the product of the K times the I times the M. The largest value of the K times the I times the M will be the lower freezing point because there's a negative sign in front of it. So since the constant is the same, now I'm going to find out what the Van't Hoff factor is for both of these. Sodium is 1 cation and chloride is 1 anion. So it's a Van't Hoff factor of 2 for sodium chloride. Potassium iodide, 1 cation, 1 anion. The Van't Hoff factor for sodium iodide is 2. That means that the Van't Hoff factor for both of these is also a constant. So now I'm looking at the molality. Okay, I have a 0.3 molal and a 0.25 molal. And so this is 0.30 and this is 0.250. Which is the larger number? Well, this one is the larger number. Therefore, it will be the lower freezing point. So which one has the lowest freezing point? 0.30 molal of NaCl. That is your answer in comparison to the potassium iodide. Okay. piece of cake, hopefully. Okay. All right. Next problem. It says, what has the higher boiling point? This one or this one, right? And so we're going to do a similar type of a conceptual problem on this one. So we have boiling point is equal to the normal boiling point plus the change in temperature of the boiling point, which is Kim again, okay? Versus, I'll do this one horizontally, the boiling point is equal to the normal boiling point plus the change in temperature of the boiling point, which is equal to Kim, remember, my college girlfriend. So it doesn't say what the solvent is. So we'll assume that the solvent is water. That means that this value right here is 100 degrees Celsius. So they have to be in the same solvent if we're going to compare these unless they were given a solvent. And then since they are in the same solvent, that means that the K is the same for both. Okay. Now I have a different molality for both of them. So the molalities are going to be different. And then the formulas, I need to check on the Van't Hoff factor. And so the Van't Hoff factor for KCl, there's one cation, one anion. The Van't Hoff factor for KCl is going to be 2. The Van't Hoff factor for BaCl2, there's one barium, one cation, and 2 chlorides, and that's a Van't Hoff factor of 3. So since the Van't Hoff factors of both of these are different, I'm going to have to include them. Then the molality is also different. So I'm going to have to incorporate that in my problem here. So the molality for the potassium chloride is 0.22, and the molality for the barium chloride is 0.15. Again, there's a constant here for both of them, and it's a plus 100, right? Plus 100 is equal to the boiling point, is equal to the boiling point. So the one that has the largest Kim has the highest boiling point. So what I need to do is take the product of 2 and 0.22. That's equal to 0.44. And then I'm going to take the product of 3 and 0.15, and that is 0.45. So which is the highest value? This is the highest value. So what has the higher boiling point? 0.15 molal BaCl2 has the highest boiling point in comparison to the 2. Okay, now I'm hoping that you saw here that what I did is I actually did not solve for the boiling point. What I did solve for is conceptually what the boiling point would be in relationship to the other one. So I'm using the concepts to solve this problem, and hopefully that's okay with you. All right? Whew. Okay. You are watching The Crazy Hat Chemist. I am The Crazy Hat Chemist. If you are learning something from this video, please note that I have many more videos online, many worked out solutions online. I have units online with videos for lectures for you as well, both in honors chemistry, which is a college prep chemistry class, which would be maybe like a first-year chemical calculations or a basic chemistry class in community college or first year. And then I also have AP chemistry, which would be the full-on, you know, like Chem 1A, Chem 1B, Chem 1C series or something like that. Okay, so please watch my YouTube videos. Here we go. We're going to go on to our next problem, which is number 9. And let's find out what number 9 has in store for us. Here we go. So here's number 9. I'm going to get just a sip of water. Okay, number 9. Let's carry on here. It says, what is the boiling point of a solution containing 24.5 grams of sodium chloride in 500 point, there's a decimal there, grams of water? The constant for the boiling point of water, which is the solvent, is 0.512 degrees Celsius, and then molality with a -1. So first of all, we're going to go over a few things here. Sodium chloride. Sodium is a group 1, that's a 1 plus charge. Chloride is a 1 minus charge, then I get the formula Na1Cl1. The Van't Hoff factor, which we're going to need to know for this problem, is that there is one cation, there's one anion, so the Van't Hoff factor for sodium chloride is a 2. Okay, the other thing over here is that we have x to the negative 1, and that is going back to your math class, this is equal to 1 over x to the first power. So that means that this molality right here, molality is negative 1 like that. That means that this is actually equal to 1 over the molality. So the units of the constant here are degrees Celsius per molality. That's how that's written there. And that's how that's written in the olden textbooks way back long ago when I was going to school, because they didn't have all these font capability that they do now. Okay. All right. So boiling point. We are going to write out the equation for the boiling point. So we are trying to solve for the boiling point. So the boiling point is equal to the normal boiling point plus the change in temperature of the boiling point. Okay, so number one, the normal boiling point of the solvent. And the solvent is going to be, we need to figure that out. So what we're going to do is we're going to compare 24.5 grams of sodium chloride in comparison to 500 grams of water. Which one has the least amount? The sodium chloride has the least amount, so the sodium chloride is the solute. Which one has the most amount? That is the water, so this is the solvent. This is one of the first things that you need to do, is you need to be comparing 24.5 compared to 500, which is in the greater amount, the 500. That's the solvent. Remember, there are 7 letters in solvent. That is in the greater amount, which has the least amount, the 24.5 in comparison to 500. That's the solute. That's in the least amount. So the NaCl is the solute. The Van't Hoff factor needs to be in comparison to the solute, okay? And the constant is based on the solvent. All right, so the solvent we know is water. And now we're going to ask ourselves, what is the normal boiling point for water? So the normal boiling point for water is 100 degrees Celsius. And since it is not given within the problem numerically, that means that we're going to assume that this is an infinite number of significant figures, because now we're going to assume that this is a definition. What we need to do now is calculate the change in temperature of the boiling point. And the change in temperature of the boiling point is equal to Kim. Remember my college girlfriend. Okay, we have the K in Kim, that's right here. We have the Van't Hoff factor for Kim, and that's right here. So what we're going to do is bring all this stuff down here. So the K for Kim is going to be 0.512 degrees Celsius per mole. The Van't Hoff factor is going to be 2. By the way, when we calculated this 2, we counted 1 cation, 1 anion. That means that this has an infinite number of significant figures. So we'll just leave that at that right there, okay? And since this is really a definition, we're going to assume that this also has an infinite number of significant figures. So the next component that I need to calculate here is the molality. Okay, so here we go, 100 degrees Celsius boiling point. Okay, so the boiling point is equal to the normal boiling point. That's 100 degrees Celsius plus the change in temperature of the boiling point. And I'm taking what the change in temperature is. That's the Kim, that's the K, that's the constant for the solvent, the I, the Van't Hoff factor for the solute, and the molality. So I need to solve for the molality. Okay, so I'm going to slide this on up here, and we are going to solve for the molality. Molality is equal to moles of solute over kilograms of solvent. Okay, and so if we go back up over here again, we have the solute is equal to the sodium chloride and the solvent is equal to the water. I'm given that the solute is 24.5 grams of sodium chloride. So I'm going to be plugging that into this right here. So we have the 24.5 grams of NaCl. This is a mass. I need to convert this into moles using the molar mass. Okay, 1 mole of NaCl. And I'm going to look at my periodic table and I am going to find sodium. That's 22.99. Chloride, that's 35.453. There's one of each of those. The sodium has 2 decimals. The chloride has 3 decimals. So I will have 2 decimals, 58.44 grams of NaCl. And that will get me the grams of NaCl will cancel out like that. Then it says that I have 500 grams of water, 500, and it was a decimal, grams of H2O. Okay, and then I need to convert this into kilograms. So my numerator here is moles. My denominator here is going to be kilograms. So 1 kilogram is equal to 1,000 grams. And this has an infinite number of significant figures for both of these because that's a definition. I'm going to cancel out grams of water. And now I will now have my denominator of kilograms. So I'm going to get a numeric value for my molality. And my molality is going to be 0.838 molal. And I'm looking at 3 significant figures, 5 significant figures for my molar, 4 significant figures for my molar mass, infinite, 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 and 3 significant figures. So this is going to have 3 significant figures. So now I'm going to put this number back up over here, 0.838 molal. Okay. And so now what I'm going to do is I'm going to plug into my calculator 100 plus 0.512 times 2 times 0.838. And since this has an infinite number of significant figures here for this normal boiling point, okay, I'm going to have 3 decimal places. This has 3 significant figures. So I'm going to have 3 decimal places because my last operation is addition. This has 3 decimal places and these are infinite. So I'm going to have 3 decimal places. So my final answer is going to be 100.858 degrees Celsius. And this is my boiling point. So I'm going to zoom on out on this problem just a little bit if I can so that you can see everything on this problem. Well, we're going to have to do this right here like this there. Then here we go. There we go. There is our problem. If it's in focus. Perfect. Okay. So this is everything on this problem. So you can see all the components to it. This is my final answer right here. This is the boiling point. So if I have 500 grams of water and if I add 24.5 grams of sodium chloride, then at 1 atmosphere pressure, then the boiling point will be 100.858 degrees Celsius. Okay, this has 3 decimal places. That's what we're looking at since this has an infinite number of significant figures. So make sure that you do this stepwise. The first thing that you need to do is compare the 2 numbers. The 2 numbers, I have the smaller number, the larger number. The smaller number is the solute. The larger number is the solvent. The constant goes with the solvent. It's almost always going to be water, okay? For the solute, I need to figure out what the Van Hoff factor is. Okay, and then I'm going to be plugging into this boiling point equation. The boiling point is equal to the normal boiling point for the solvent. So I got to go back to what is the solvent? What's the normal boiling point for water? That's 100. And since it's not given in the problem, that's defined at an exact number. And then it's the change in temperature of the boiling point, and that's equal to Kim. So I'm going to divide this up into really small little steps. I'm given the constant for the solvent. I'm going to write that down. That's the K for the constant. I figured out what the Van 't Hoff factor is. That's an infinite number of significant figures because I counted it, one cation, one anion. And the most difficult part here is solving for the molality, and that is down here below here is solving for the molality. And that is the moles of solute over the kilograms of solvent. So do this stepwise individually. And I got my mass of solute, and I'm going to divide by the molar mass. That will give me my moles in my numerator term. And I want to get divided by the kilograms of solvent. So I take my mass of the solvent, and I'm going to convert that grams into kilograms. And then I'm going to do the moles divided by the kilograms, and I'm going to get a molality, and I'm going to plug that right back into here. Then it's 100 exact number plus the K, the I, and the M, and the product of these. And then I'm going to add that to the normal boiling point. Fantastic. So hopefully you should see that you should get that. And then you should be also asking yourself a question. Now, is the normal boiling point higher than, is the final boiling point with the solute in it higher than the normal boiling point? It better be a yes. Okay, you cannot get a boiling point when you add a solute to a solvent that is less than the normal boiling point. Impossible, okay? All right. All right, so we're going to pull this one away. We're going to do the next problem. The next problem is going to be a freezing point problem. So let's see what we can do with that one and hammer that one out. All right. So I'm going to zoom in here a little bit here like I had before so we can see this and you can see all the parts here a little bit better. Here we go. All right, fantastic. All right, so here's our problem, number 10. It says, what is the freezing point of a solution containing 82 grams of ethylene glycol? And I give you the formula because I don't expect you to know that. In 500 with a decimal grams of water, and it's the constant for the freezing point. I've already talked about this -1 in the previous problem, so hopefully that's okay for you. That goes in the denominator. I'm going to set this one up in a similar fashion that I did on the last problem, and hopefully that will be okay for you. Okay. So here we go. Freezing point is equal to the normal freezing point minus the change in temperature of the freezing point. Okay, and what we're going to do is we're going to cross out the change in temperature of the freezing point because that is going to equal what? That's going to equal Kim. So hopefully that makes sense. So what we have to do is figure out what is the solute, what is the solvent. So I have a number here and a number here. Okay, I'm going to compare these two numbers, 82 and 500. Which is the smallest number? Ethylene glycol, smaller number. Which is the larger number? 500, that's the larger number. The smaller number is the solute. The larger number is the solvent. So I have now delineated what is the solute, what is the solvent. The normal freezing point is referencing the solvent. So the solvent is water. The normal freezing point for water is going to be 0 degrees Celsius. That is going to be an exact number because it's not given within the problem anywhere. And I am trying to solve for the freezing point. So the normal freezing point is 0 for water. That's why I have that in there. Minus K, the constant, is 1.86 degrees Celsius per molal. And then ethylene glycol. I'm giving you the formula here. And if you follow my lecture, go to my lecture on YouTube for this unit here. And if you go to that, then you should see that the Van 't Hoff factor of this compound is equal to 1 because this is a molecular compound. And so this is 1. The Van 't Hoff factor, so this is the K, that's the constant. This is the Van 't Hoff factor. The Van 't Hoff factor is a counting number, so it has an infinite number of significant figures. We'll assume that this constant is infinite. We'll assume that this is a counting number, which it is, and that's constant. And this is an exact number, and that is also infinite. Now what I have to do is get my molality, and that will be my next part in the chem. All right. All right, so here we go. I'll do this just slightly differently than I did on the last problem here. So it gives you another option of how to solve these problems, but not really a whole lot different because you really can't do too much that's different. All right, so what we need to do is solve for the molality, and then we're going to take the product of the K, the I, the M, and subtract that from 0. And we're going to hopefully we better get a negative number because you're going to get a number that is less than the normal freezing point of the solvent if you add a solute to it. Always, 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 always. Okay. So the molality. Molality is equal to the moles of the solute over the kilograms of solvent. So what we're going to do is do this maybe just a little bit differently than last time. And I'm going to take the 82 grams of C2H6O2. By the way, ethylene glycol, that is the major component to antifreeze that goes in your radiator of your car. So I'm going to find the molar mass for carbon. That's right over here, 12.011. The molar mass for oxygen, that's 16.00. The molar mass for hydrogen, 1.0079. Hydrogen has 4 decimal places. Oxygen has 2, and carbon has 3. So the least number of decimal places is 2. So therefore, the molar mass is going to be rounded to 2 decimal places, and that is right here. 62.07 C2H6O2, and that's equal to 1 mole. C2H6O2. So I'm going to plug this into my calculator. I have 2 significant figures, 4 significant figures, and an infinite number of significant figures. So the number that I get in my calculator is a 1.3 moles of C2H6O2. And that's the moles of the solute. All right, now I'm going to get the kilograms of the solvent. So I'm going to take my 500 decimal grams of H2O, and I'm going to convert this into the kilograms. So let me zoom this out just a little bit so I can fit this all on one page here. Here we go. 1,000 grams of H2O is equal to 1 kilogram, and this is an infinite number of significant figures. Infinite, and this is a 3 because of that fantastic decimal right there. And this is going to equal, what will this equal? 0.500 kilograms of H2O. Okay, perfect. So what we want to do now is we are going to take the moles of the solute divided by the kilograms of solvent. So I'm going to take this number divided by this number, and that's going to equal my molality. So let's see. I'm going to do that right up here in black up to the side here. So molality is equal to 1.3 moles of solute divided by 0.500 kilograms of solvent. And that number is going to equal 2.6 molal. And that number is going to go right here, right there. 2.6 molal. So that's the moles of the solute, which is the ethylene glycol, divided by the kilograms of the solvent, and that is the water. All right, and now what we're going to do is we're going to take 0 minus 1.86 times 1, that's 1.86, times 2.6. That's going to equal, this whole thing right here is going to equal 4.8. Okay, and we are going to take 0 minus 4.8. So we're going to have negative 4.8 degrees Celsius. There is my freezing point if I have 500 grams of water and I have added 82 grams of ethylene glycol to that. Oh my. All right, fantastic. Hopefully that went well for you too. And you are hopefully learning something. Again, if you are learning something from these units, these videos, then please give me a thumbs up. I'd greatly appreciate that. Please pass them on to, maybe you have some friends that are going to take chemistry in the future, pass them on to them, or you have, a cousin or something like that that's going to take chemistry in another country or something like that, then pass it on to them as well. Anyways. All right, here we go. We are going to go on to our next problem. So I'm going to peel this away and we're going to slap on the next problem here. Boom. Here we go. And it says, what mass of barium chloride must be added to 45 mils of water to have a boiling point of 102.000 degrees Celsius, and the boiling point constant is 0.12 degrees Celsius per molal. And I've already talked about that -1 there. All right, so let's see here. So the first thing that we're going to do, actually, is we're going to say a boiling point is equal to the normal boiling point minus the change in temperature of the boiling point. Okay, so we need to figure out what is the solute, what is the solvent. Okay, it says that we have water and barium chloride. Barium chloride is BaCl2. That's a group 2 barium and chloride halogen, and that is the solute. It has a Van't Hoff factor of 3 because barium, there is 1 cation, that's the barium. There are 2 chlorides, and that's 1 plus 2. That is a Van't Hoff factor of 3. Okay, so it gives you the boiling point of the solution. So I'm going to plug that in right into there, and then we know the normal boiling point of water, so we're actually going to solve for the change in temperature of the boiling point. So this is 102.000, I think that's 3 zeros, is equal to 100 minus change in temperature of the boiling point. Okay. So we're going to subtract 100 from both sides, and we're going to get the change in temperature of the boiling point is equal to 2.000. Okay, remember, this 100 is a defined value, and that's an infinite number of significant figures. So that means that this is going to have 3 decimals on it. Okay, so then the other thing is the change in temperature of the boiling point is equal to Kim. So that means that this is equal to Kim. This is equal to Kim. Okay, so our change in temperature of the boiling point is equal to Kim. All right, so what we're going to do is we're going to plug into here. We have 2.000 degrees Celsius is equal to K. The K is given right here in this problem. That's 0.512 degrees Celsius per molal times the Van't Hoff factor, which I just solved for you up here, and that is a 3 times the molality. Okay, now I've seen students solve this problem in many different ways. We could break up that molality term into little bits and pieces here, and that is the moles of the solute divided by the kilograms of solvent. But actually, it's going to be easiest if we just solve for the molality here. So we're going to solve for the molality. We're going to divide both sides by 0.512 and 3. 0.512 and 3. So now we're going to get the molality is equal to 1.30 molal. Okay. All right. And now we need to know the definition of molality. And so the definition of molality is that 1.30 molal is equal to the moles of the solute, that's barium chloride, divided by kilograms of solvent, that's water. What is the denominator of this number? 1. What is this denominator? 1. All right. Hopefully that works for you. Okay. Wait a second. Maybe that didn't work for you because maybe you didn't see all that. So I'm going to slide this up. What's the denominator for this number? 1. What's the denominator for this when I break it up into its moles per kilogram? 1 in the denominator. Okay. Now what we're going to do is we're going to slide this on up here. We are going to be using these 45 mils of water. Okay. And we're going to be calculating the mass of barium chloride. Okay. So we're going to slide this on up. Okay, and well, let me come back down here, and we'll do one more thing here first before we slide this down completely. All right, so we have 45.0 mils of water. Does anybody know the density of water? Well, you need to know the temperature, but without knowing the temperature, we're going to make an assumption since this is not ice. We're going to say that the density of water is 1 gram per 1 mil. Okay, This is a key component here. This is a unit conversion, an infinite number of significant figures. The mils cancel out. And then I'm going to convert this into kilograms. So that is 1,000 grams, 1 kilogram. So this right here will be my kilograms of a solvent of which I have, which is 0.0450 kilograms of H2O. Okay, so that is 45.0 times 1 divided by 1 times 1 divided by 1,000, and I get this value here. That is the solvent. Okay. Now what we're going to do is we're going to slide this up. So ultimately what we're trying to do is get the mass of the solute, which is the barium chloride. Okay. And so I'm going to slide this on up right over here, and I'm going to be using this concept right here. Okay. I have 1.30 moles of BaCl2. And this is really a stoichiometry problem at this point in time. Okay. That's a 2 right there. This is in 1 kilogram of H2O. That's a defined infinite number of significant figures. Okay. And we want to get the mass of this. So, well, what do we use? The molar mass. 1 mole of barium chloride is equal to the molar mass, and that's 208.24 grams of BaCl2. And that is, we're going to cancel out the moles of barium chloride. This will actually get you the mass of barium chloride for 1 kilogram, but I don't actually have 1 kilogram. What do I have? I have 0.045 kilograms. So 0.0450 kilograms of H2O. This will enable me to cancel out kilograms of water. And then I'm going to say 1.30 times 208.24 times 0.045, and that will equal, what will that equal? That will equal 12.2 grams BaCl2. Fantastic. So that is the mass of barium chloride that will be added to this. So let me zoom on out here so you can see the problem in its entirety. So there's the whole entire problem right. Let's see if we can get this on here on one screen. There we go. There's the problem in its entirety right there. So just to recap real briefly, we were given the boiling point. We know the normal boiling point of the water, which is the solvent. We are going to solve for the change in temperature of the boiling point. So we subtracted the normal boiling point. We got the change in temperature of the boiling point. We said that's equal to Kim because the change in temperature is equal to Kim. So we've got our our change in temperature of the boiling point. We got the K for Kim. We got the I for the solute, and we're going to solve for the molality. We solve for the molality. We broke that apart based on its definition, and that's moles of solute per kilogram of solvent. We know that the number in the denominator is a 1. And then we brought that back over here like that. Okay, we're trying to find out the mass of that solute, so we're going to multiply by the molar mass. That answer right here would just give you the mass in 1 kilogram, but I don't have 1 kilogram. I have 45 mils. We're going to use the density of H2O, and that's 1 gram per 1 mil. We learned that a long time ago. And then we're going to use our unit conversion to get to kilograms. And then we're going to multiply by that kilograms. That will cancel out our denominator there. And then we finally have the mass of barium chloride that would be added to 500 to 45 mils of water to get a boiling point of 102. Okay, fantastic. All right, we're going to slide that off over here, and we are going to move on to our next problem here. And I'm going to zoom back in here and move this around so we get all the parts in here in one screen so it looks nice and pretty. All right, there we go. Now we are on problem number 12. Okay, so here we go with problem number 12. Here we go. It says, calculate the mole fraction of sodium chloride for a solution that contains 25 grams of sodium chloride, that's NaCl, in 62 grams of water, and calculate the mole fraction of water in the same solution. All right, so we're calculating the mole fraction of sodium chloride and the mole fraction of water. We're going to calculate the mole fraction of both. So mole fraction is, I have to get moles. It's not a mass fraction, so I have to get moles of both. So we're going to take 25 grams of NaCl, and we are going to calculate the moles of NaCl. So we're going to look on our periodic table and get the molar mass for sodium chloride. That's 22.99 times 1, 35.453 for the chloride. And we're going to round that to 2 decimals. So that is 58.44 grams NaCl. That's equal to 1 mole of NaCl. And then I'm going to take 25 grams divided by 58.44, and I'm going to get 0.43 moles of NaCl. So that's the moles of the sodium chloride. All right, now what I need to do is get the moles of the water. So that's 62 grams of H2O. And then I'm going to get the molar mass for water. And that's 1.0079 for hydrogen times 2 plus 16.00 for oxygen. And I have 2 decimals on that for the oxygen. That's 18.02 grams H2O. And that will equal 3.4 moles of H2O. So now that I have the moles of both the solute, this is the solute, and this is the solvent. The solute is in the lesser quantity, the solvent is in the greater quantity, and you can even compare the mole values with the solute and the solvent and get that as well. Okay, the mole fraction is not a mole percentage, it's a mole fraction. So what we're going to do is say mole fraction of NaCl is equal to the moles of the sodium chloride, that's 0.43 moles of NaCl, divided by the total moles, which is 0.43 moles of NaCl plus 3.4 moles of H2O. That is going to equal a number from our calculator. And so we're going to get that, and it's 0.43 divided by 0.43 plus 3.4. Make sure that you're not dividing just by the 0.43. Okay, and that will equal 0.11, and that's the mole fraction. There's no units to that. That's the moles cancel out. Boom, done. Now we're going to get the mole fraction of H2O, and that's going to be the moles of the water, that is 3.4 moles of water, divided by the total moles, so that's 0.43 moles of NaCl plus 3.4 moles of H2O, and that number is going to be 0.89. I'm using 2 significant figures on both of these numbers. All right, and so now I have the mole fraction of both the sodium chloride and the water. And then what you need to do now is to make sure that you have done this correctly, and that is the mole fraction of NaCl plus the mole fraction of H2O. That should equal a 1. And so I'm going to take 0.11 plus 0.89, and that will equal 1. If it doesn't equal 1, then you probably did that problem wrong, and that would be a bad thing, and then you're going to start over and try it again. Okay? That would be my check on that problem. All right. Sweet. All right. We are going to move on to the next problem. All right. The next problem, let's see, is number 13. And let's slide this up here a bit. It says, the solubility of a gas in water is 0.14 grams per liter. Remember that negative exponent 1 at 125 kilopascals. What is the solubility when the pressure of the gas is increased to 185 kilopascals? Assume the temperature remains constant. That's an important thing. This is a Henry's law problem. So Henry's law deals with the solubility of gases. And so therefore, we're going to be using the Henry's law equation, which is effectively solubility of gas 1 over the pressure of gas 1 is equal to the solubility of that same gas under a different set of solubilities and pressures. So I'm going to be solving or using this Henry's law relationship here on this. So I have 0.14 grams per liter over 125 kilopascals. Notice that it's 0.14 grams per liter at that pressure is equal to, and I'm trying to find for the solubility under a different pressure, if I've increased the pressure in this case of kilopascals. What I'm going to do is I'm going to make sure that my units of kilopascals are the same. It doesn't matter what the units are, but as long as they are the same. I'm going to cross multiply. Okay, so it's going to be mathematically 0.14 times 185 divided by 125, and I'm going to get the solubility of the gas, and I'm going to have two significant figures, 0.21 grams per liter, and there's my answer. Fantastic. That one should have been super simple. All right, so we're going to move this on up here. There we go. And we're going to do problem number 14. 14, it says determine the mass necessary in grams of a 50 mil, 50.0 mil solution of a 0.15 molar ammonium hydroxide. So we have our molarity again. And so we're going to do this. We're going to say 50 mils, trying to do these a little bit differently each time. 1,000 mils is equal to 1 liter. This is equal to 0.0500 liters. I'm maintaining these zeros, which are trailing at the end, and then these are leading zeros. Leading zeros never count. Okay, I'm given a molarity, which is 0.15 molar. That is equal to 0.0500 liters. And I'm going to solve for X, which is the moles of the solute. So remember, the denominator of every number is 1. I'm going to crisscross applesauce and solve for X moles. So the moles... that's 0.15 times 0.0500 is equal to the following here. That would equal to 0.0075 moles of ammonium hydroxide. That's ammonium ion and hydroxide ion. That's ammonium hydroxide. And I'm trying to get the mass of this. And the mass, 1 mole of ammonium hydroxide. And now I'm going to get the molar mass of ammonium hydroxide, which is 1 nitrogen, 14.007, times 5 hydrogens, 1.0079, plus 1 oxygen. And that would be 35.05 grams of ammonium hydroxide. And then I'm going to take that number, 0.0075 times 35.05, and I'm going to get an answer with 2 significant figures, 4 significant figures, infinite number of significant figures, and you're going to get an answer. Oh, wait, did I tell you to watch my videos on YouTube? And if you're enjoying this and you're learning something, give me a thumbs up and please subscribe to my YouTube channel. Okay, good. You're going to have a number in 2 significant figures. So that is going to be 0.26 grams of NH4OH. That is your answer. Oh, yeah. Yes. Okay. Next one. So I'm going to peel this away, and we are going to do number 15. We are cruising now, folks. We are certainly cruising. Peel this page away here. There we go. All right, next one is number 15. It says, what volume in milliliters is necessary to make 500 mils of And remember, we talked about this of before, and that's a multiplication of hydrochloric acid, hydrochloric acid, that's HCl, and that's aqueous, solution from a 12.0 molar stock solution. So this is a dilution problem. So dilution is the solution to pollution. That's a really bad thing to say, but you know, it's funny and sad at the same time. That's what we used to do in industry many years ago. We don't do that anymore. Molarity 1 times volume 1 is equal to molarity 2 times volume 2. So the first molarity is 0.150 molar. My volume of that is 500 with a decimal milliliters. And my concentrated stock solution, maybe not old, but 12.0 molar. And I'm solving for the volume 2. It says what volume in milliliters is necessary of that 12 molar stock. Okay, and so what we're going to do, very simple problem here, folks. 12.0 molar. I am dividing by that. The molarities cancel out. My volume of my 12 molar stock solution is 6.25 milliliters. I have three significant figures of 12.0 molar HCl stock that's necessary. By the way, it didn't ask for it in this problem, but how much water is necessary? So that would be 500 mils total volume minus the 6.25 mils of the stock would equal the amount of water that is necessary, and that's 494 mils of water that is necessary. Even though that question was not asked, I asked it on a previous question. Might as well get to know that too, right? Nothing wrong with that. You should be getting to know that. All right. Oh, yeah. Remember, you were watching The Crazy Hat Chemist, and I am crazy just to be making these videos because I'm not even sure if anybody actually watches these crazy videos. But if you are out there, watching my crazy videos, I would greatly appreciate it if you subscribe to my YouTube channel and pass it on to your friends in other countries. Tell them to subscribe. Tell them to watch. Tell friends in other schools to watch. Tell them to subscribe. I would greatly appreciate that. That would be fantastic. Anyways, little advertisement plug for myself. Can't help it. All right, now we're going to do problem number 16. All right. You know, you notice that this is my table right over here. It's wood. You know, we can't afford very much, so we just got to have wood tables, you know. I mean, but I like the old wood, and that's what this is, an old wood table. They're beautiful. So, yeah. Here we go. Problem number 16. Okie doke. I'm gonna give myself a little bit of a break here, walk around the block. All right, folks, here's what we're gonna do. I'm gonna break this video up into two videos. And so we're gonna continue on with the next video. So this is gonna be part 1 of part 2, I think. So yeah, that's what we're gonna do. All right, so we will see you for problem number 16 next time. Love ya. Have a good day. Bye now.